So hi everyone, so a while ago I made a video about how to automatically detect walls, doors and windows from floor plan images. So maybe one thing that was a bit missing from the algorithm was that how we can automatically determine the scale of the floor plan. And by scale I mean what is like the conversion from pixels to meters, which is pretty much which is very essential part of every analysis that we perform on floor plans. So one very rough way to do the estimate the scale is to use the fact that the standard door is around 0.9 meters wide, and if we can know know the width or length in pixels, so we can use these facts to determine the scale. So in this tutorial I was planning to use the object detection, the most traditional one, the faster RCN neural network, to determine the bounding boxes around the doors and then use this information to determine the scale. So I decided to divide this tutorial in three parts. So in this first part we simply go through to the data generation and how to efficiently load that on PyTorch. And then in the second part of the tutorial we go through the basic faster RCN network and see how far we can get with that. And then finally in the third part of the tutorial we use the more advanced feature pyramid based faster RCN and see what we get from that. Okay, so to get started with data we need the training data. So essentially the input data are like this, so there are bitmaps, and then the ground truths are like this, so you can see the red boxes that marks the doorways. So what we essentially would like to eventually have is this kind of annotations.json file. So what we would like to have is that we would like to have like the source image name and then the corresponding bounding boxes. So the bounding box is always informed or announced as a kind of the minimum and maximum corners. So to generate the annotation we could simply use some annotation software that is available on online free and simply draw the rectangles around the door and save the results. However, I would like to avoid this step, and instead I was planning to use the existing ground truths for the semantic segmentations. So we of course can directly use this ground truth here for the bounding box regression, because in this format the ground truth shows each pixel that corresponds to door, but it doesn't tell you the actual bounding box. However, I was planning to create a Python script which simply draws the minimum bounding box around each of these boxes. So what we can do here is that we can simply use this kind of connected component analysis. So what does the connected component means? It means that essentially it divides this image into these wide regions, and then we can simply determine the extents of that region. So let's see how we can do that in Python. So here I create this kind of small Python script that we can use to do the task. So let's see how does it actually work. Okay, so let's run the script and let's see what happens. So here we got the original input image, and then here we got the semantic segmentation ground truth, and here are some the connected components based on this ground truth image. So essentially what is in this ground truth image, we can see that we got different regions labeled from 1, 2, 3 to 4, and then we have drawn this blue rectangle around each of these, which is essentially our bounding box. So let's see what the code actually do. So here we simply load our input data for the ground truth and the original image. And then the essential part is here, so we use this label function from scikit image. So what does this do is that this determines kind of similar regions from the image. So if two neighboring pixels has the same value, so then it kind of groups them in the same group. And this is what we see here, so because it's shown here. And then what we do later here is that we simply loop over all of these labels, and then on this line here we determine all the pixels that corresponds to certain label. So it means that we pick all the pixels in this region, and then we simply determine the minimum and the maximum values, and then we simply add those values into our bounding boxes, which is our ground truth. And then later what happens in the script is that for this network to work, each of these images need to be about same sized. So for that reason we need to do some splitting here. So we determine the target size, which I specify as 1024 times 1024. It's quite big, but it's okay because this happens in kind of offline. So essentially I did this kind of boilerplate code to do the splitting. We could have use some bill crop or something like that, but well, it's here now. And the essential result is that we get these images of same size, and then we get this annotations.json file here. So for example, for the first image, we can see that we got 4 boxes corresponding to these four door openings, so it seems to be correct. And yeah, and then the next step is when we got the data available here, so the next step is to see how we can efficiently load that in PyTorch during the training. Okay, so let's look the data loading in PyTorch. So for that purpose, I have created this class called object detection dataset, which inherits the torch dataset. So why we want to do this is that we can give this dataset as input to this torch data loader, which then automatically handles the data loading for a given batch size, and then it can essentially parallelize that efficiently given the number of workers. Here I'm simply using the num workers as 0 because for debugging it doesn't work properly otherwise. But let's quickly see what happens when we run the iterate over the data here. So okay, so let's see the result. So okay, so here we get this bit messy looking image. The reason why this look like this is that the data loader, it normalized the image. We will look soon more closer to that, but what we essentially see here is that there's the input image, a bit weird color space, but essentially we get the ground truths here. And in debugger we can see that what are the image and the target. So we can see that the image is actually a list of tensors, and each of if these tensors, they corresponds to the image, and we got 2 tensors here because the batch size was given as 2. And then what's are in the target? So in the target we got again we got the list, and then each item in the list is again it's actually a dictionary where boxes are the bounding box coordinates, and then labels means in which class they corresponds, and because we simply only have a door, so there's just a simple class and it's number 1. Okay, but let's see what actually happens here. So let's put okay, let's see a bit about what the construction is. So here we one partner is this root data path, so it simply points to this folder where all the data lies. And then maybe other key component here is this transfer function. So what we can see here is that we need to normalize it, and what are these mystic values here is that we use the ResNet from PyTorch in the faster RCNN, and it requires this normalization. So the normalization of the input image need to match the pre-trained white on that ResNet, and that's why we got these transformations. But then one necessary function in this dataset is this getItem function. So it determines that given the parameter IDX, so it uploads that bounding box. So what happens here is that we simply take we have uploaded the annotations, and then we simply pick the image at location IDX and open it. And here's this kind of the correct way to do here is that we would like to do some data augmentation, but let's not go there yet. Let's go there a bit later when we actually get training, but we're happy with this right now. And yeah, and then we in a similar way we read the bounding boxes, and then we simply iterate over each bounding boxes, and then we create this target structure here, and then finally we return the image and the target. And here we are using before returning the image, we are transforming it properly, and then that's pretty much it. And then the PyTorch data loader, it automatically handles the path sizing and stuff like that. And the nice thing is also this number of workers parameter, which enables automatic kind of parallelization of data loading. But yeah, that's pretty much that for the first part of the tutorial. So next time we look about the actual faster RCNN implementation and how to train it using the Google Colab. So thanks for the attention.